Hello chemistry students. This video is meant to be an extension of our large group lecture from Wednesday, and it should be completed by you during your PLT time, and it's going to give you a basis to follow for the rest of your packet. The first topic that we're going to talk about is scientific notation. And basically what scientific notation is, it's a way for us to write only the significant figures of a large or small number. In standard scientific notation, it's usually a number, or always is a number, from 1 to 9, followed by a decimal and the remaining significant figures, and it has an exponent to hold place value. An example of this would be 5.43 times 10 to the second. Now this is the same as writing 543. You can see from this example that we have a number 543 that we are writing as a number from 1 to 9, but we still hold the same number of significant figures. So there's 3 significant figures in each problem. Now, how far we move this decimal place is what dictates this number in the exponent right here. And I'll get into more on that later here. Another example of significant figures would be 8.65 times 10 to the negative third. When you see this negative third, it means we have moved our decimal point in the opposite direction. Now this number is equal to 0.00865. Now that we have a basic understanding of what scientific notation is, we're going to practice writing a couple of numbers in scientific notation. Let's say, for instance, we have the number 65,000. What we are trying to do is we are trying to write this as a number from 1 to 9 while still maintaining the same number of significant figures. So what we need to do is we need to move the decimal place from right here, and we need to make this a number between 1 and 9. So we're going to move it 1, 2, 3, 4 places to make this 6.5. The number of places that we move the decimal point is going to be equal to our exponent. So we would write this as 6.5 times 10 to the fourth. If we do one more example and we do 7,060, first we need to figure out how many places we need to move this decimal point. So we're going to need to move it 1, 2, 3 places. Now we need to preserve our number of significant figures, so we need to write this as 7.06, and since we move the decimal point 3 places, our exponent will be 3. So we write times 10 to the third. We can do this with numbers that are less than 1 as well. So if we have a number that is less than 1, or basically if we move the decimal place to the right, it makes the exponent smaller for each place that is moved. So for example, if we have a number such as 0.00043, and we want to write this in scientific notation, we still need to make a number between 1 and 9. So what we would do is we move this decimal point 1, 2, 3, 4 places to the right. So this would become 4.3. And now since we move it to the right, it is going to become a negative number, or we subtract 1. So we would say this is 4.3 times 10 to the minus fourth. So now you should have everything that you need to know to complete the scientific notation part of your packet. On the following slides, you will learn how to add and subtract using significant figures and multiply and divide using significant figures. Before we do that, I just wanted to quickly review what Mr. Gussie talked about in Wednesday in large group, and that was the Atlantic Pacific rule. And this is going to help us determine the number of significant figures in a number. So very briefly, we said if there's a decimal point that equals present or the Pacific side of the United States. So we're going to start on the left side of a number. So we would count, and we don't start counting significant figures until we get to the first non-zero number. So this zero doesn't count, this zero doesn't count, doesn't count, doesn't count. So we have 1, 2 significant figures in this problem. So I'd write 2 significant figures here. Now, if the decimal point is absent, we start on the Atlantic side, and we don't start counting until we get to our first significant digit. So this zero doesn't count, this zero doesn't count, and we get to the first non-zero, so there's 1, 2 significant figures. Now, the third one down, we have a decimal point, so we start counting at the first non-zero digit. So we start at the 2, and we have 1, 2, 3, 4 significant figures. And in the very last one, we have a decimal point present again. We don't start counting until we get to the first non-zero number. So this zero doesn't count, this zero doesn't count, neither does this zero nor this zero. We start at the 2, so we have 1, 2, 3, 4, 5 significant figures. All right, sig figs in math. If we are going to multiply and divide with significant figures, it is relatively easy. Literally the hardest part of these type of problems is figuring out how many significant figures are in the numbers that you're working with. So, your final answer here has to have as many significant figures as the least precise number, or the number with the fewest amount of significant figures in the problem. So the very first thing that you need to do is figure out what's the least amount of significant figures in the problem. So using our method from before, we have a decimal point present in both our first two numbers, so that's 4.56 and times 1.4. So we need to figure out how many significant figures are in each of these. Well, there's a decimal point present, so we count for the 4.56, and there's 1, 2, 3 significant figures here. So we write 3 significant figures. If we look at 1.4, there's 1, 2 significant figures. So we write 2 on top. If we multiply 4.56 times 1.4, our answer should equal 6.38. But knowing what we know now, our answer can only have as many sig figs as the number with the fewest amount of sig figs in the problem. So that would be 1.4. Therefore, our answer must only have 2 significant figures. So if we look, we need to round this up to 6.4. In the next problem down, you'll see here that we have to figure out how many significant figures always are in the 2 things that we're multiplying. So we look here, we have 1, 2, 3 significant figures, and 1, 2, 3 significant figures. And although when we multiply the 2, we have an answer that has 4, we must round to 3 significant figures. So this number becomes 4,830. Addition and subtraction of significant figures is slightly different than multiplying and dividing significant figures. The main difference here is that our final answer must have the same number of decimal places as the least precise measurement used in the calculation. The easiest way to see this is by example. So, if I were to write out 41.2 plus 36 plus 10, we would first have to determine which is the least precise measurement. And basically, it's where the last significant decimal place is. If we look here, the last significant digit in one of these problems is the 1 in 10 here, because we don't count this 0 as a significant figure. So we must round our final answer to the tens place. So if we were going to add this all up, we would add 0.2, 7, and then 4 plus 3 is 7, and we would have 87.2. But we must round only to the place to the left of this blue line. So our answer must be rounded up to 90 to hold for significant figures. This is because, once again, 10 is the least precise measurement used in this calculation. Here we have another example, same type of thing with addition again. The least precise measurement is always going to be the measurement with the fewest amount of decimal places here. So if you look at this next example problem, 18.0, right, is the least precise measurement in this problem, and that's because it has the least amount of decimal places. So in this instance, our answer must be rounded to the tenths place. So we've added these all up, and it becomes 31.123. We must round to the tenths place, so our answer becomes 31.1. That is everything that you should need to know to complete the Sig Figs and mathematics portion of your packet, which can be found on the 5th page. The last thing that we need to discuss for today is how to take proper measurements. This is found number 11 in your packet, and it's on the second side of your packet. When taking measurements, first things first, if you have a beaker like this, we need to talk about where you read a measurement. And what you need to do is you need to read from the bottom of this meniscus down here. So you'd be reading right from down here, and it needs to be at eye level. So if you look, this meniscus is right around, I would call it probably 24. Another thing to realize when you are making a measurement, your measurement cannot be estimated past one place more than your instrument is calibrated for. What I mean by that is, if you look at this beaker, it is calibrated out to the tenths place. So we have 10, 20, 30, and 40. So that means that I cannot say reasonably that that is 24.95. I can only estimate that out to the ones place. So I would have to either say it is 24 or 25. Because this beaker does have a place for the fives, it's probably within reason for me to say that this is about 24.5 though. Our next example is a graduated cylinder. If you look at this graduated cylinder here, you'll notice first that it's actually calibrated out to the ones place, which is one further than our beaker was. Now it is reasonable for me to estimate to what would be the tenths place. So I still read from the bottom of the meniscus, and if I look here, it's a little underneath what would be the 53 line. So it is reasonable for me to say that this would be about 52.9 milliliters. When I am reading a graduated cylinder or a burette, it is important that my eye be at the direct level of the meniscus, the bottom part of the liquid here. The reason being is because if it's not, as you can see from this picture, it is going to throw off my measurement. If I'm looking from too high, my measurement will be lower than it should be. If I'm looking from underneath the meniscus, my measurement will be higher than it should be. And you can see that if I'm looking directly at eye level with the meniscus, I will get the right reading. Last type of measurement that I like to go over is a burette. Now, a burette is actually the opposite of a graduated cylinder. It's read in the opposite direction. So it is actually read from top to bottom instead of bottom to top. So it actually, numbers increase as you move down the burette, and that's because we let liquid out of the bottom. So if we're looking at our burette here, we read from the bottom of the meniscus here, but instead of moving down as we move down the burette, we actually are moving up in volume as we move down the burette. So if we're looking at this one, this would be about 40.5 milliliters. This will conclude the lesson that we have completed in large group on Wednesday. You now have all the information required to complete pages 3, most of 4, and 5 in your packet. Accuracy versus precision and percent error will be covered on either Friday or Monday of this following week. If you have any questions on this video or any of the material covered, please feel free to stop by, ask me, or to ask one of your teachers during lab in the following days.